So today we're going to start chapter 18, and we'll go, hopefully get through about halfway today, and then when we come back from spring break, so remember that next week is spring break. Yay. So we do not, yeah, you didn't know. So we will not be meeting for class. I mean, campus is open, but there won't be any classes. So when we come back from spring break, which will be on Monday the 13th, then we'll continue with chapter 18, and we will then have a problem-solving session, the following week review, and then the exam will be that following Wednesday. So we still have 3 weeks from today before the exam. So, but again, take the time if you feel like you might be a little bit behind in your classes, not just this class, but do take the time of spring break as an opportunity to get a little bit caught back up. But it is a break, so also rest a bit and come back refreshed. But chapter 18 is now on the derivatives of carboxylic acid. So remember that the carboxylic acid has that OH, right? Well, the derivatives, that OH is going to be replaced by a variety of different groups. So for instance, a chlorine makes it an acid chloride. Okay, really two acids together makes an acid anhydride, right? We did look at some esters last time with the esterification, Fischer Esterification reaction. So OR, right, a carbon chain here would be another derivative. And then you can also have nitrogen derivatives like an amide, right, which can also be a nitrile. We can convert these into each other, so we'll look at that. And if you notice, all of these derivatives really come from the reaction of the carboxylic acid, right, with a certain group, right? And the product is always, right, a water with it. So you're really doing, right, a dehydration reaction. So you're removing a water, right? And then you get from the carboxylic acid, so it's involved in all of these, except for, like I said, the nitrile really comes from the previous reaction. But the first four, you can see the carboxylic acid being involved, and then you're removing, right, the water. Does everybody see the pattern again? Right, there's a pattern to this, so we're not really learning, right, a lot of different reactions, but you do want to realize now that this is a water, right, is getting removed each time, right? You see it in the yellow. Okay? And so that's what we're going to do in this chapter, is really study these derivatives. Okay, so the chlorides, the anhydrides, the ester, and the amides. And so let's start with the acid chloride. So the functional group, again, now is going to have a double bond O, which when it's attached to an R, we call an acyl group. So just the C double bond O is called a carbonyl. But when there's a carbon chain associated with it, it gets a separate name called acyl. So you might see these as like acylation reactions because it comes from the acyl group being involved. So just a good definition there to know. The acyl group has an R attached to the carbonyl. And so the chloride, the acid chloride, is an acyl group and then a Cl attached to that. Does that make sense? So we really, because all of these derivatives come from the carboxylic acid, the naming also comes from that. So when we look at this, this comes from acetic acid, would you agree? Or ethanoic acid, right? 2 carbons. If you had the OH, it would be ethanoic acid or acetic acid, right? So we usually, for this, we drop the ic acid, so keep the O, and then you're going to add YL halide, right? In this case, chloride. So it becomes ethanoyl, so leave the O, right? Ethanoyl chloride. Does that make sense? From acetic acid, it would be acetyl chloride. Does that make sense, what we're doing there? So if it was ethanoic acid, right, leave the O there. You're going to get rid of the ic acid, right? You're going to get rid of this part, and then you're going to add YL, and then whatever your halide is. Usually we're going to focus on the chlorides for this chapter, even though you can have bromides and iodides and whatnot. Does that make sense, how to name these? There's going to be a lot of naming in this chapter. So would you agree this comes from benzoic acid? Right, a benzene ring with the C double bond O over here, right, OH. Okay, so, but we substituted that, so we dropped the ic acid, so instead of benzoic acid, it becomes benzoyl chloride. Does that make sense? So this is going to be dioic acid, right, since there's 2 of them. So we get 6 carbons if you count, so hexane, right, so hexane dioyl chloride, because again, there's 2. Does that make sense? Naming there? So these are the acid chlorides, and again, they can be halides, but usually in this chapter, we'll just see the Cl version. Okay, you can also have sulfur, so sulfonyl chloride. So instead of a C double bond to O, right, the acyl group, you'll have this sulfonic acid. That's where it's coming from, right? So we substitute again the OH with the Cl, right? So 1 carbon is methane sulfonyl chloride, right? This is toluene, right? The benzene with the CH3. So again, toluene sulfonic acid becomes sulfonyl chloride, right? And YP, because they're 1,4 from each other, right? So ortho, meta, para, there are positions, non-numerical positions. Okay, but again, your
Ortho is
ortho is right next to, if they were 1 and 2. Meta would be 1 and 3. Para is 1 and 4. So those are non-numerical. Yeah, question?
So basically, we're naming it the same way. So ic acid, we're doing Lyle chloride.
Yeah, so you're basically, in this one, you actually get rid of the NIC, just because the sulfonic acid, there's an N there, but you're keeping the O and then adding YL, right? Or I'm sorry, the N is there.
Yeah.
Sulfonyl, I think I dropped it when I said it, but yeah, drop the ic acid, you're right, and then YL and the chloride. Yeah. So. But this is with the sulfur, so there's also these sulfonyl chloride derivatives that can form. And then the anhydrides is basically 2 acids together, okay, and we'll see how we make those also, but basically, again, right, comes from acetic acid since you have 2 carbons, right, and so this becomes acetic, and because there's 2 of them, they're called anhydrides. So the O is in the middle, and then the 2, right, acyl groups on each side. Again, if we look at this looks like it came from benzoic acid, right? So this becomes benzoic, 2 of them is anhydride. Make sense? So in this case, you're dropping the acid, right? Keep the first part and adding anhydride. And these are symmetrical, but they don't have to be. They could be mixed. Okay, then the name is a little bit more complex, but again, we won't see many mixed. Now, I don't know if Al might throw in a mixed, but I would not do that on the exam. Because if it was mixed, you would have to say both sides and then anhydride. So it's not that hard, but it just, you wouldn't have just a single name there. So acid anhydrides. And then the anhydrides can also be cyclic, so you could actually, if you had it already connected here, write 2 acids in a linear fashion coming together. So the O would be holding the 2 acyls together as part of a ring. Okay, and so these are called cyclic anhydrides. And again, they come from 2 carboxylic acids. So this is succinic because there are 4 carbons. Okay, maleic, there's 4 carbons with a double bond. And then phthalate, you have the double ring. So you have a benzene and, right, the cyclic anhydride together. So these, unfortunately, you just have to memorize these 3 names. So, but these are the only 3 that you will see as examples, right? So then esters, right? So remember esters, this came from the acid, this came from the alcohol. That's how we put esters together. Acid plus alcohol gives you an ester plus water. We talked about that last time. So again, you drop the ic acid, and now you're going to add 8. Okay, so you name what came from the alcohol, which is an ethyl, this side, right? And then the other side, right, is also ethyl, but it came from ethanoic acid. Drop the ic acid and add 8. So ethyl ethanoate, right? And so in this case, you have 2 of them. Ethyl, Et is ethyl. You have 2 of them, so diethyl came from the alcohols. And then 1, 2, 3, right, propane, there's 2 of them, so dioate, right, came from dioic acid. So esters, okay, 8 is the new ending. And then esters can also be cyclic, so again, you see the, right, acyl here next to the O, right, but they came together as part of the same structure. Okay, so you had an acid and an alcohol. And so these are called lactones. Okay, so cyclic esters. And so for the naming, you're going to drop oic acid and add O-lactone. So 1, 2, 3, 1, 2, 3, and then 4, right? So butanolactone. That makes sense. Okay, so why the 3?
Because
this is actually a substituent coming off of the ring. So it's telling you, yes, it's 4 carbons, but that, right, 3 position has a carbon coming off of the chain. So that's why you see the 3 there. Okay. And then this one is 1, 2, 3, 4, right, all as part of the ring. Okay. So why is it a 4?
Because you count the 4, the 1's always going to be the double bond up.
So the 4, no, the 4 is always going to be connected to the oxygen here. So it's locating that oxygen in this one. Okay, so what about this one? 1, 2, 3, 4, 5, 6, right? So hexane, lactone, hexanolactone, excuse me, and then you get 6 for where the oxygen is. So I think I misspoke in the first one. I'm sorry, the 3 here is not telling you, it's locating the O. I didn't read all the way here. So the 3 is locating the O, which makes the carbon have to go out of the ring. So, but the 3, just like the 4, just like the 6, is locating where, right, what carbon the oxygen is attaching to the ring. So that's lactones. And then amides are carbonyl, right, the acyl with a nitrogen now. Okay, so those are amides. So remember, amines is just the nitrogen, okay, with a carbon chain. So now it's amide with a D. Okay, so drop the oic acid from the parent acid and then add amide to it. So again, this came from acetic acid, so I'm dropping the ic acid and saying acetic, right, acetamide. Right, so drop the ic, so acetamide. And then these, right, this is just primary. The nitrogen only has hydrogens attached, but what if the nitrogen had a methyl attached? So you also have to make sure that's clear. So what you're actually going to say is this methyl is attached to the nitrogen. So you say N for nitrogen as a locator for where the methyl is. And then this is the acetic part, right? Acetic acid part. So that's acetamide. Does that make sense? So N-methyl for this part, and then acetamide, just like here, right, for the acetic acid. Okay. And then here, what would I say? I now have 2 methyls, right? So I say NN. They're both coming off of the nitrogen, and I have 2 of them, so dimethyl. Sense. And then this is only 1 carbon, so it comes from formic acid, so formamide, which is also known as DMF. It's a very common solvent that we use in organic chemistry. So the N becomes the locator if there are carbons coming off of the nitrogen. Does that make sense? What the N means? And then you have cyclic amides, and these are called lactams. Have you heard of lactams somewhere before? Beta lactams? Anywhere before? Penicillins? That's why people are allergic to penicillins, usually because of the beta lactam, and also that's what causes them to be, the bacteria to get resistant to them, is this beta lactam ring here. And so this is, again, right, so cyclic, because you have the acyl, right, and the nitrogen, but it's part of the same molecule, so they became cyclized. And so again, 4 carbons, 1, 2, 3, 4, right, locate where the nitrogen is, so 3-butanyl, and then lactam is now the naming, right, drop the ic acid, add lactam, okay, and then again over here you have 6, right, 6 is where the nitrogen is, so 6-hexanyl lactam. So the beta really comes from, right, that second position. Alpha is right next to, and then beta is at the 3 position. So that's where penicillins get their structure, is based on this beta lactam. All the penicillins have this same, right, structure. And then other sides can be different. Right over here, you can change things over here to make different, like penicillin G and penicillin B, and like there's different generations of penicillins. I think there's actually 6 or so generations of lactam antibiotics of different penicillins. But again, all of them have the beta lactam over here, right? So now you know what it is. It's that amide as a cyclic. Does that make sense? So, and this happens to be amoxicillin. Cephalosporin is another class of antibiotics, and they have also that beta-lactam ring, but you have 2 parts that you can change over here, just like the penicillin, but you can also change over on this ring side, since it's a 6-membered ring. It's very stable for modifications over here, so cephalosporin is more resistant, right? It doesn't become bacteria don't have as much resistance, I guess is a better way of saying it, because you're not just substituting one thing, but you're substituting 2 things, so the bacteria has a hard time figuring out, right, what to do.
So what does that mean?
Tricky.
What does that mean?
That means, you know, when a bacteria is resistant to an antibiotic, that means it doesn't do you any good to take that antibiotic anymore. And so what's happening is that so many, like bacteria, have become resistant to antibiotics, like we're going to one day not have treatment for bacterial infections anymore. So that's a big, big problem. So that would be the end of medicine, really, as far as antibiotics are concerned, like no way of treating bacterial infections, and that's a very scary place to be. Right? You could die from something really simple just because you don't have treatment for it, because the bacteria have become resistant to the antibiotics. So there's a lot of documentaries about that. There are what they call superbugs, and these superbugs, they're originating in India. Why do you think in India? What's wrong with India? Not wrong, but what? Overpopulated, right? And not very, the sanitation isn't, good like it is here as a third world country. So lots of people in an area where there's, a lot of waste. So they already exist. And there was a case in Philadelphia, and there was also a case at NIH in Washington of superbugs in hospitals in the U.S. So watch some documentaries. It's pretty scary. Or take my microbiology class this summer, and you'll be able to. Another plug. Today I'm full of plugs. I'll keep that on the video there. So we talk about that. We actually watched one of the documentaries that was a Frontline documentary. That's from PBS. Airs those. So there's one on 3 cases of superbugs that had impact here in the U.S. So one of them, the person was in India and they got hit by a train, and both of their legs, I think, got cut off. So then they got an infection, and of course he was transported here to get treatment, but he was infected by one of these superbugs, and now he's in a hospital here in the U.S. Right? So
how did he get hit by a train?
He was standing like too close, and he actually got pulled in. There's a suction that happens when a train goes by, and if you're standing too close, you can actually get sucked in by that. And so that's what happened. He wasn't standing on the tracks, he was standing on the side and got pulled in. A friend of mine, that happened, she got hit by a fire truck. Same thing, she was standing too close, and the fire truck came so fast, and it pulled her into the truck, and she hit the side of the truck. She's all right though, but. So things like that, it wasn't an honest mistake. He wasn't standing on the tracks or anything. So go and look, Frontline. It was actually on Netflix for a while. and you could just, you know, watch it through there, but I don't know if it's still available like that. But I think you can go to PBS and watch old Frontlines for free, since it's public, you know, access. So. All right, so then Amides, so now, right, the lactams have one acyl group in the nitrogen. This has two acyl groups, and then the nitrogen in the middle. Okay, and so these are called amides. And again, you just have to memorize a few of these. But succinamide, right, has 4, right? And then the phthalimide, again, that has the benzene, right, with the double ring here with the amide on there. So those are double rings. And then the nitriles, which come from the amides, so there are reactions that can convert this, but remember nitriles are C triple bonded to nitrogen. Okay, so again, you name what it's attached to, right, the acid that it originated, drop the ic acid and keep the O nitrile, right, so ethane nitrile, right, or acetyl nitrile. This is from benzoic acid, so again, right, benzo nitrile. And then this is, right, this is the acid part. The phenyl is a substituent, so phenyl nitrile, right, or phenylacetyl-nitrile. So again, it comes from this base here. So another example there. So let's practice. So what's the first thing you have to do? Right, lots of naming in this chapter, so we do want to do a little practice, and I'll just send you off here. But what's the first thing you have to do? Identify what? The functional group, actually. So you kind of want to start there. I know usually we start by counting carbons, but since there's so much variety, the first thing to me that I would suggest is saying, okay, right, what kind of functional group is this? Is it a carboxylic acid? Is it an ester? Is it an amide? Is it, right? Like which one? It's an ester, right? C double bond O, O, and then an R group. So then you can kind of go to the ester page and say, okay, how do I name an ester? Do you remember how to name? If not, go back, because you have to do this by yourself, right? So you name the part that came from the alcohol, which is Me, is methyl, right? So methyl, and then you name what came from the acid, which was 1, 2, 3, 4, right? 3-methyl butanoic acid, right? So drop the ic acid and add ATE. Does that make sense? So methyl, 3-methyl butanoate. Does that make sense? So you name the part that came from the alcohol all the way in the front. So it starts with methyl.
Wait, so we put methyl.
Methyl, and then because there's a substituent which happens to be a methyl, right? This is 3-methyl,
Oh, so
and
methyl,
then it's 4 carbons. Not methyl-methyl, but methyl,
3-methyl.
and then 3-methyl, because that's part of the name of the acid. Right? So they should be
Methyl, 3-methyl.
like methyl, and then you have a 3-methyl,
Butanoate.
and then it's butano, right? You keep the O, and you add ATE,
What's
which is the
ATE
ending.
for?
S is the ending for an ester. The suffix for an ester is ATE.
So you name the part coming off the S, methyl, first.
The O stays, you just drop the ic acid. That's how the naming is. So yeah, you name the part that came from the alcohol, which is usually together with the single bond O, whatever that is, up at the very front. Then you deal with the name of the acid, which in this case is 3, right, methyl butanoic acid. But you drop the ic acid and you add ATE. So 3-methyl butanoate. I don't know if I have answers. So they go together. So nobody saw that. So what's B? Is B still an ester? Or is it something else?
There's an ester and
It's still an ester, right? And it has this ketone, right? So the ester is higher priority because it's a carboxylic acid derivative. So how do I name this again? So what do I do first? Ethyl first, right? The part that came from the alcohol, ethyl. And now it's 1, 2, 3. What's this as a substituent? Oxo. 5. 3-oxo-butanoate. Does that make sense? So the ethyl first, right, because that's the part that came from the alcohol. You got to do that at the very beginning. Then you deal with the part that came from the acid, which has an oxo group, right, a ketone at carbon 3. So 3-oxo-butanoate. But again, you got to identify as an ester first, like, or at least that would be my suggestion. You know, you can really do whatever you want, but I think this is helpful. So what's C? What kind of functional group? Amide, right? So that makes sense. An acyl with the nitrogen. But there's not just one, but two, right? So it's carbons, right? 1, 2, 3, 4, 5, 6.
So 1, 6,
so hexenamide, but you have two of them, right? So 1, 6, hexane diamide. And you don't have to number, I guess. I must have looked it up, but it doesn't hurt to put the locators, but usually when you have two, like, you know, you see the locators, but I guess you don't need. So hexane, and you can put NE here, it doesn't hurt either, it's just for pronunciation. And then, but it is di, 2 amides, right? So diamide. And because it pops up together here, it's already there. But again, if you look at this, hopefully you see this, the two together, right? 2 acids. So that's anhydride. Okay, but this is 2 carbons, right? 1, 2, 1, 2. And then the phenyl is a substituent. So phenyl, right? Ethano, right? The ethanoic here. Ethanoic, and then anhydride is the name of the two together. So phenyl as a substituent, so phenyl. And then it's 2 carbons, so ethanoic, and then anhydride because it's 2 of them put together.
So phenyl, ethanoic.
You don't have to say in the anhydride if they're symmetrical, if both sides are identical, you don't have to say di. You just name it one time. When they're mixed, then you have to put 2 names up at the beginning, but they're symmetrical. Does that make sense though? So lots of naming on this coming exam. So there's lots of options of naming. It's still just going to be one question for 10 points, but there's just a lot of variety. So, you know, might be in your best interest to, you know, kind of keep these all together because there's carboxylic acids, right? Also that we did aldehydes and ketones before this chapter, right? And now we have all these derivatives also. As a so naming, and then now for some chemical properties. So the first one we want to start with is usually acidity. So acidity here is of the nitrogen bond when we talk about amides, right? Or right when we talk about the amides. So these are, and of course we didn't actually have a slide for this, but remember that you can have the sulfonic chlorides, you can also have the sulfonyl amides. So you can use sulfur as a substitute for the carbonyl here. So these hydrogens here, that's basically what, you know, this slide is saying. These hydrogens attached to the nitrogen are considered to be acidic. So you can see the pKa's here, right? Okay. But of course, right, being between 2 carbonyls really increases the acidity. So the amides are going to be better acids than the amides, right? And of course the sulfur also helps. Because this is about neutral, right? This would be the same as an alcohol in water, right? 15, 16. But the more, right? More here with 2 double bond O's, right? 2 double bond O's, more double bond O's does increase the acidity, right? By decreasing here, the pKa is showing you that. So you can do a number of acid-base type reactions with these. So for instance, the amide shown here, in this one is not only right, these two together, but you also have the double bonds from that benzene ring, so there's a lot of opportunity for resonance structure. So you can kind of see there, okay, just some examples of that. So the more resonance structures you can draw, the better, right, your acid is going to be, because it's going to be stabilizing your anion, right? This charge on the nitrogen here, you can see that I can move it to the oxygens, right? Can put it over here, right? Can move the double bonds around. So there's, right, electron withdrawing inductive effects, and you have this delocalization going on. So you should consider the amides as acids. So you'll be able to draw reactions like this, right? With a base, a strong base, like sodium hydroxide here, right? The amide would give you an acid-base reaction, right? So the hydrogen from the acid is going to go to the OH of the base, form water, right? And then you would get the salt of your acid, right? The sodium there. That makes sense? So what if this was an O in the middle? Would it be able to do this? If instead of an NH, it was an O? No, there wouldn't be a hydrogen attached to that O, because O only makes 2 bonds, right? So this doesn't work for oxygen, for the oxygen analog.
It wouldn't work for esters.
Wouldn't work for the esters. Okay, and then just as a, oh, sorry, go ahead.
I was going to ask, is that how you make, like, salicylic?
How do you make
Like salicylic acid in acetylsolid form?
salicylic acid is in aspirin in the like pill form? Or salicylic acid, I'm sorry, it's not aspirin, it's acetylsalicylic acid, but salicylic acid is solid, yeah. It's,
Yeah. Is that how you make it? Kind of, you know?
well, salicylic acid doesn't look like this. It's not cyclic like this. Salicylic acid, it's a benzene ring and it has an acid group, and then it also has an alcohol group. So this is salicylic acid. And then we do the reaction here to form aspirin. So we'll do that eventually in lab. So salicylic acid is not, you know, something like this cyclic. I don't know if I answered your question. So it's just, it's different here, type of reaction. So when we go, but saccharin is an example of an amide, well, a modified amide. It's an artificial sweetener, you might have heard of, right, saccharin. And this is, again, right, you have that nitrogen in between, right, those double bond O's, but it's modified, so it has a sulfur here, right, instead of having another carbonyl. So that's why it's not really recognized as naturally occurring, right, but your taste buds will taste sweet, right, but you'll be able to do those acid-base reactions. So they didn't give you the pKa, but do you think the pKa is going to be, right, this is 8.3. What do you think of having this over here? It's going to lower a little bit, right? So again, it's a very good acid. So it's soluble, which is important too. This has to be soluble if we're going to be able to consume it, right? And it dissolves in, right, the liquid that you're putting the sweetener in. So this is just an example of something we use daily that is a modified amide. Okay, but really the key reaction in this chapter, so again, the theme, right? You want to think of the theme. So what was the theme for aldehydes and ketones again? What was the theme for aldehydes and ketones? What did we do? What kind of reactions did we do? Nucleophilic additions, right? So when you had either an aldehyde or a ketone, right, you would get a nucleophile that would attack, right, but you had the double bond that would open. Does that make sense? So you would have the same thing here. So the nucleophile would attack, double bond would open. So the product would give me what? 4 bonds, right? So it's an addition, right, plus the nucleophile. Does that make sense? Right, that just in general terms, that was our right theme. Okay. But the theme is a little bit different now because you have something over here that we label Y, and Y can leave. So you're still seeing the same pattern, right? Nucleophile attacks, double bond opens, right? You get your 4 bonds, right? Of course, you add an acid to complete the hydrogen here, so you get an alcohol plus the nucleophile. Does that make sense? So far it's the same theme, okay? But I want you to keep in mind that Y can be eliminated. So there's an addition, just like this. This is an addition. Does that make sense? Right? This is an addition. Because carbons don't leave, do they? They're not good leaving groups, are they? Right? Carbons nor hydrogens, right? That makes sense? But this Y thing is not a carbon and it's not a hydrogen, right? We just saw a bunch of derivatives, right? These derivatives have leaving groups. The chlorides, right? The halides. That's a great leaving group, isn't it? A Cl, right? This is a great leaving group as a carboxylate. Okay, this is okay, right? This is from an alcohol. It's not great, but we can transform it into a number of different leaving groups. We saw that in chapter 10, right? And then nitrogen, it's not great, okay? But it's still, right, can leave because nitrogen will carry the negative charge. So basically, the main difference between chapter 16, right, this is chapter 16, and chapter 18 is what? The leaving group, right? The fact that you have this leaving group, right? Does that make sense?
Yes.
So are you going to get this as a product? A 4-bonded carbon? No. Okay, you're going to reform the carbonyl, so we'll see that in just a minute. Okay, so of course, what is the best, right, leaving group? The halides, the acid chlorides are going to be the most reactive at these addition eliminations, okay? But you see that this is increasing. So this is good too, right? This is all right. This is not great. So some reactions don't happen with the amides because of that, because NH2 is not that good at leaving. Okay, but we'll talk about that. So the halide ion is the best leaving group. Therefore, the acid halides are going to be the most reactive. Okay, and like I said, the amide ion is not a very good leaving group. It would leave, but not under certain conditions. You really have to, have the right conditions. So that's going to be considered the least reactive. So if I was, ranking the derivatives by reactivity, the most reactive would be the one with the best leaving group. Does that make sense? And then the one that was the worst, right, the least reactive would be the one with the poorest leaving group. So that's what this slide is telling you. Does that make sense? So that's really just ranking them here. Right? So let's say that I wanted to react, right, with water. So acid, right, acetyl chloride, right, would be my best bet. This is the most reactive because it has a great leaving group. Does that make sense? So what's the nucleophile of water? OH, right? OH minus. I mean, it's going to attack, right, as a nucleophile, right? That's all I'm saying. So this is going to add an OH here, right? But it's not really an addition because this is going to open, close, and the leaving group is going to leave. So see how the product still has my acyl part. It's not an alcohol like this. Let me just complete it just for the sake, right? Okay? It's not the single bond O. I get my double bond O back. And how did I do it? Just like I said, you attack, right? OH is going to be your nucleophile. This is going to open, but then it's going to close because chlorine will be happy to leave. Does that make sense? So I added something, but then I also eliminated something, right? And what did I eliminate but the Cl, right? An H from here and a Cl from here makes your HCl byproduct. Does that make sense? How these reactions, and all of the reactions in this chapter follow the same pattern. nucleophile attack, open, close, leave. That's how I think of it. When I see a reaction like this, I think, okay, this is going to come, attack, this is going to open, just like this. But because there's a leaving group, this is going to close back up. Double bond, still there. And then the leaving group is gone. That makes sense? The theme, right? Because that's going to happen over and over and over again. And because this is such a great leaving group, this is a very rapid reaction. This is a very, boom, 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 you got, okay, this product. And the product of a reaction with water is the carboxylic acid again. So it kind of goes back, right, to the original acid, so the carboxylic acid. Does that make sense? But of course, the second line, this is for small, low molecular weight means small. But if this carbon chain gets really long, the problem is that they're not soluble in water. So when they become insoluble, it's harder to do this reaction because the reaction is in water, right? And so, so this works best when your acid chloride is small. Okay? Now, what about anhydrides? Would you think this will continue to be a good, fast reaction? Yeah, right? This carbonate ion, right? So one of these again, right? The water, the OH is going to attack, right? Open, close. One of these is going to leave. That makes sense? So the leaving group is an O, C double bond OCH3. One side, right, is the leaving group. Again, the H comes from water, right? The OH that you added is here. That makes sense? So you get two of the same, right? But you got one from the attack, right? And one from the leaving group. That makes sense? No. Okay. Can you see that these are two of the same, right? These are anhydrides, so they're identical to each other. So it doesn't matter which one I attack, you're going to get the same product, but space it out a little bit here, right? So water is the nucleophile, right? Which is really OH minus, right? So this is going to come, attack, right? That means this has to open as a double bond. We know that's how the reaction has to start. It's an addition to start. But then, right, this can close back up into a double bond, which means this is going to leave. So the leaving group is really this side, right? And I've already used up my OH, but I have an H plus from water that's hanging around, right? So this is going to come together to form one of the products, right? The other side gets the OH right here as the nucleophile, and it makes the other one. Does that make sense? Okay, and these are still really good reactions. They still react very rapidly with water. And again, there has the high molecular weight, the larger it gets, the less soluble, so the harder the reaction is. But
So because this is such a good leaving group, the molecule splits. It's already pretty much symmetrical. It just splits.
well, it doesn't split automatically. It
Yeah,
splits
because of
when the addition happens.
File.
But yes, this is symmetrical, so it's going to split at the oxygen, which is holding the two together. But
Because it's a good leaving group.
because it's a good leaving group, so that's the key, right? It's a good leaving group. So what about, so this is the steps here. And my question is this acid catalyzed or base catalyzed? How do I know?
DO.
Is it acid or base? Who thinks it's acid? Only Brooke? Cheyenne? You there? Is it acid or base? Acid. How do we know? How do you know?
H3O+.
It's protonating, right? See how the O of the double bond is going to pick up the hydrogen? That's a protonation reaction. Only happens when you have an acid, right? And this is O3, right? This is the hydronium ion, which indicates an acid in water, right? So this is acid catalyzed, right? So again, you do this just to make it even more reactive. Then water can come in and attack. It doesn't have to be a hydroxide, right? But then it forms, right? An oxonium ion, which an additional water molecule, which is circulating, comes in and takes out the hydrogen, right? So now you have it here. And then the tetrahedral intermediate collapses, so you can see that it closes back up, right? So you can see it's, I mean, it's a complex process, but again, the key here is to make this close, right? So that this side can leave. So you're breaking the bonds here. So I like my way. Would this happen in base? Yay or nay? Would this happen in a base environment? Yay or nay? So if I was back over here, right? Would this happen if I had a base? Where's the base going to actually target?
The first carbon right there. Yeah.
No, right? Because that's not where I want a base, because this is next to a carbonyl. This is the alpha position is acidic, so I don't do these reactions in base.
So bases would only work with aldehydes.
Yes, aldehydes and ketones then, but those can also, because they have, if they have an alpha, so I wouldn't say that. I retract my answer to that. It depends on what aldehyde you have and what ketone. Ketones, yeah, no good. So bases, but do you get the point? The base is gonna target your alpha position, and that's not what you want here. So these usually don't. So what about esters? Would you think this reaction would happen for an ester?
No.
So think about the leaving group. Now the leaving group is getting bad, right? Now it doesn't mean it cannot happen. What it means is I have to make my leaving group better. So remember, with alcohols, that means protonation. So the ester is a slow reaction, even when you heat it pretty high, boil, right? So what it means is you have to have an acid catalyst. You have to. You don't have to have an acid catalyst for these. You really don't, these two. You can. It helps if you add an acid. It definitely does on this one. But you don't have to. Do you even want an acid in this one? No, because you produce an acid as a byproduct, right? And that would be a competing thing. So the acid chloride, you don't even want an acid. It's just going to happen, right? With the anhydride, an acid will help, but it's not needed, necessary. But with the esters, it's not going to happen without an acid, because the acid is going to guarantee a good leaving group, right? So how, right? How is it going to do that? So the acid catalyzed, what is the acid going to do? Here, right? To give you the alcohol. Does that make sense? Because this acidified, it didn't show you all the steps, right? But this took the H, made it plus this open, right, to give you this with the OH attached, right? So again, you have to have it so that this will form. Now, can you do reactions of esters and bases? Yes, you can, but these reactions are of a different kind. They're hydrolysis reactions. So you can break up an ester with a base. You cannot make an ester with a base. So each mole of ester can actually break up, or each mole of base with the ester can break up the bond, and what you get is a salt plus the alcohol. So this side of the molecule, right? The CH3 plus the OH give you the alcohol, and then the O minus, right, gets associated with the sodium plus to give you the salt. Okay? And so this is called a hydrolysis reaction. Okay? And so hydrolysis is just in water though, right? This is in base. So the hydrolysis is going to form this tetrahedral addition intermediate, right? But then it's going to collapse and have a proton transfer. So the question I leave you with, since we're out of time, is how. So we'll get into that next time.
Next one.
We'll talk about that next time. So again, next week. Okay, so really what we want to consider in this chapter again, and that's hopefully what the first part was getting you to think about, is when you have, right, something like this, this here is considered the leaving group, right? And so that kind of sets up a different kind of reaction than what we saw in chapter 16, right? Because in chapter 16, the carbonyl was either next to a hydrogen or next to a carbon chain. And neither of those are what we would consider a leaving group. So, you know, the key with chapter 18 is to remember that you're still going to have that nucleophile, right, attacking, right, opening this up. That's still the same. We saw that in chapter 16 also. But the difference is the double bond can reform because the leaving group will leave, right? And so in part A, you wanted to consider that, right, the chlorine is the leaving group, right? The carbon of the carbonyl is still the group being attacked, right? Does that make sense? And so, and of course, if you have an acid, right, the protonation is going to be on the oxygen of the carbonyl. And again, that gives that additional, right, force to break that double bond between the carbon and the oxygen. So that's kind of, you know, what you want to consider in this chapter as we continue on here with the reactions. And I know 10 days is a long time. I could not for the life of me remember where we stopped, but is this close? I should have watched my video to remind myself of did you mark by, did anybody kind of like notes kind of stop? Am I close?
Stopped at the
What chapter are we on?
arrows. Oh no.
There?
Got to
Oh,
here.
I thought I did all
What
that.
chapter are we on?
30, yeah, I thought we did this already, but I was just gonna kind of refresh with this. Yeah, I thought we got to the, through all of the reactions with the water, right? And so really, right, previous to this, what we were doing is nucleophile was water, right? So we did it with the acid chloride, we did it with the anhydride, we did it with the ester, we did it with the amide, right? So the nucleophile was water, right? Which in the case of water is really a hydroxide ion. Does that make sense? So that's the set of reactions before this. This is, okay, now that you have an ester, so the ester, okay, can be reacted, right, with water in two different ways. One is a hydrolysis reaction, again, if the OH is, right, coming in as the nucleophile for water. And that's really the reverse of that esterification, the Fischer esterification reaction that we saw earlier, okay? And so, again, the water, right, acting as the nucleophile. But you can also have this second reaction, which is a similar reaction to hydrolysis, but it is not with water, but with base, right? So if now the nucleophile is NaOH, right? That makes sense? It could be KOH also, something like that. So it's a similar reaction. You're still going to break that ester bond, okay? But the bond breaks a little bit different. You're not transferring really the OH to the carbonyl in this reaction. What you're doing is actually transferring the OH to the carbon chain to give you the alcohol. So the oxygen stays with the carbonyl, which is not exactly the same, right? And so the Na then couples as an ion, right? The oxygen is negatively charged, the sodium ion is positively charged, so they interact as an ion, right? Ion pair or a salt, okay? And so the difference here again, instead of the bond breaking here, which is what we would expect with the reactions we just saw, okay? You're going to break the bond on the other side of the oxygen. So the sulfonification reaction, okay, that's in presence of a base. So it's a little bit different there. Okay, so this is the how coming up here. So how does this happen? Right, so the hydroxide does attack, as you see there, okay, and you do have that leaving, but you notice that the O minus of the alcohol is going to come back and remove that H here, okay, leaving it as the ion. So when you think about the reaction, it is similar in mechanism, but the products are very different. So that's really, you know, the key between the hydrolysis and the sulfonification reaction. So again, hydrolysis is in water, sulfonification is in base. Does that make sense? So, those are the ester reactions. Okay, and then the amides, okay, coming next here. So what happens when, okay, you add water to the amide? Okay, it's also a hydrolysis situation. So again, right, amide, okay, carbonyl next to that nitrogen. You're adding water. Okay, now this reaction, remember that the nitrogen is not a great leaving group. It's the least, right, on your table that we gave you. That's the one that's least likely to leave. And so you do need some help. You need an acid catalyst and you need heat. So this reaction happens, but it's not, okay, as easy to happen as with the other groups.
So you have to have heat for this reaction.
For this reaction, you would have to have heat. And for the ester, you need a catalyst. Okay, and sometimes, I mean, you can heat those reactions. When we make aspirin, we heat that. That's a similar type of reaction. But you definitely, this would not go forward without heat, though. This nitrogen is not a very good leaving group. Okay, but again, if it leaves, right, it leaves, okay, the nitrogen leaves because of the attack, right, of the nucleophile, and then what you get is that salt, right, so the ammonium chloride, again, you have the, right, chlorine from your acid, or the chloride, excuse me, from your acid, okay, and then the nitrogen it leaves, okay, as that ammonium chloride ion. But again, this is, right, not a very robust reaction, again, because nitrogen is not a good leaving group. So can this happen in a base situation? And the answer is yes. So you can also do this with a base catalyst. So you see here, right, sodium hydroxide, again, right, some heat required. Okay. And so in this case, the nitrogen here, okay, it's not just an H2, but it's, right, attached to the phenyl. Okay, is this good or bad for the leaving group? It's actually good because you have conjugation. So the reason nitrogen doesn't leave, is not as good of a leaving group, is because the negative charge on the nitrogen, okay, is not as easily carried as the oxygen. So by having those double bonds, I can disperse the negative charge, and that's good. So this is actually helpful. The size, right, you might have thought about that. I mean, it's kind of a bulky leaving group, but the question of, you know, whether a leaving group is good or bad is how well the atom, right, in this case nitrogen, is going to handle the negative charge it's going to have once it, you know, is an ion. So in this case, the phenyl is actually helping. So that's what's happening here. So again, the leaving group is still, though, the nitrogen, you understand, right? It's just this time it has the phenyl attached. So again, you're going to attack, open, close, and then this whole thing leaves. And when it leaves, right, it's the nitrogen with the phenyl. That's called aniline. And we talked about that in the naming. And of course, this is in base, so it's not a hydrolysis, but a sulfonification, so you get the salt of your acid. Right? So in the presence of a base, either sodium hydroxide, potassium hydroxide, you form the salt. And I won't go through this mechanism here, but it is on page 723 and 724 if you want more detail. But of course, I wouldn't ask you this on the exam since I'm not going over the mechanism. It's really, if it's helpful for you, okay, you can take a look at the mechanism. It is available in the book. Okay, so this is the one with the nitrogen, the NH2. Okay, so again, in the presence of an acid, remember that what's going to happen is protonation of the oxygen of the carbonyl. So you see the hydrogen, right? So you create that ion, the O with the plus charge. And then, of course, there's resonance associated. Okay, and that's what stabilizes it. And it creates, right, that shift base there that you see. Okay, and then eventually what happens is the water then can come in as the nucleophile attack. Okay, so that's the next step here, addition of the water, so it's the nucleophilic attack. And then of course, since you have a leaving group, right, which was transformed to the ion, NH3 here, so that's the leaving group, right, you can close the double bond, leaving group leaves, okay, but you do still have an ion here, so the nitrogen is going to act as a base, which we know ammonia is a good base, so ammonia is going to pick up the hydrogen, and now you have your two products. Remember that the product is the ammonium ion. So this is displayed there as the products. Does that make sense? Again, right, when you look at something like this, it's complex, but you're focusing on what's the nucleophile, what's the leaving group, right? Because that's going to lead you to the final product. If you know what the nucleophile is, right, of water, OH, and you know that the nitrogen is your leaving group, then you're going to get the correct product. So that's really the key steps there. And then of course nitrile is the other group here, and nitriles really, they go hand in hand with the amides, and so they're not that reactive. Okay, so they're kind of in the same category. A lot of the reactions we're going to talk about, amides and nitriles don't undergo because they're just not good leaving groups. But you can see here with water, you can also take the nitrile. Okay, again, water, acid catalyst, some heat, right? So same conditions as the amides. And then again, you'll get the acid, right? Water, the nucleophile is the hydroxide, the OH, and then you get the ammonium salt. So really, main difference here is probably the amount of water. I think it's only one, it's 1-to-1 with the amide. And here's 2 waters, okay, because you do have a double bond, a triple bond, excuse me, right, that has to be converted to a double, and then the process is the same after that. So nitriles usually go hand in hand, so this is, again, in base, so the sulfonification reaction, you get the salt, right, and again, the leaving group gets converted to the nitrogen, the ammonia in this case. And then in the bottom is just showing you that you can convert the salt from the sulfonification reaction into the acid if you would like. All you have to do is add some protons. Then the protons are going to associate with the oxygen, form the acid, and then the Na, right, will couple with the chloride. Sodium chloride will then be formed. So if if you're doing sulfonification, there's still a way of getting an acid. Okay, you just have to add one more step with an addition of an acid in water or a dilute acid. Does that make sense? The water reactions. And then why? And so this just shows you some other ways of converting. So again, why use nitriles versus using amides or things like that. So just to consider that you can convert them to the acid, just like I showed you before. So again, you can take something like 1-chlorobutane, right? It's an easy SN2 reaction here to do the substitution. You're substituting chlorine with a cyanide, right? So or the nitrile group, and then you can convert it using the steps we just saw to get the acid. So it's a really simple conversion. Same thing here, an aldehyde, right? You can add again the cyanide. Okay, you're going to attack. This is going to be the nucleophile, right? Open. There's no leaving group, so the OH is still there, right? But then you can do acid in water to get your acid product, your carboxylic acid. So that's the useful part, is that it's easy to use nitrile as a nucleophile as well, right? Because it can attack and do SN2 type reactions or do acyl, right, nucleophilic addition there as well. So we do see a lot of reactions like that. So those are the reactions with water. So again, what's the nucleophile of water? The OH, right? So now, what if we were using alcohols? What if our nucleophile now is coming from alcohol? What is that going to be? OR. Does that make sense? Right, so that's kind of what you want to consider, right? If you're doing a reaction, right, plus water, right, what's the nucleophile, right? The nucleophile is going to be an OH minus, right? If you're adding an alcohol, right, your nucleophile is going to be, right, O, and then an R chain. Does that make sense? Again, negative charge, right? Does that make sense? So that's kind of the kind of thinking you want to have as you're going into these reactions. So now we're going to see that as our, right, nucleophile. So here's our most reactive acid derivative, right? Chlorine is an excellent leaving group, right? So again, you're going to look at this and say, okay, that's an alcohol, so I know that the O is going to attack, right? Taking with it that cyclohexane, right? Right? Open, close, leave, right? So what you're adding is this, right? Make sense? So if you understand the concept of what's the nucleophile, and of course you identify the leaving group that is associated with these derivatives of chapter 18, right? It's not hard to see what the product is going to be, right? The O plus your R group, in this case, is a cyclohexane, right? And that's going to get attached to your carbonyl. Does that make sense? And then, of course, you have the H and the CO, right? The leaving group plus the hydrogen forming HCl. Yeah.
You said the double bond open and closes again?
It opens, right? It makes, right? But it breaks at first when the nucleophile attacks, but because there's a leaving group, it can reform back into the carbonyl. Does that make sense? Okay, and so just a few, considerations again, right? Acid halides, that's going to be pretty good reaction. This is, a good leaving group, so this reaction is great. Okay, now some alcohols are sensitive to the HCl. So, you're forming HCl as this reaction is progressing. So as the reaction goes on, some of your alcohol might end up, right, reacting with the HCl, and that's bad for your yield. And so if that's the case, if you, have a sensitive ester, or I'm sorry, did I say alcohol? Sorry. Your product can be sensitive, and so make sure. Yeah, either the alcohol or the ester. What I'm saying is, let's say this H wants to come back and participate in the reaction. That's a problem, right? Because that's a catalyst. And so that can decrease our yield. So if we think that's going to be the case, we can always add a base, which a tertiary amine is going to be a good candidate. So that's what that statement is telling you. So usually you'll see pyridine or triethylamine in this reaction for that reason, to neutralize the acid that's produced. And so that's really only a concern with the acid chlorides, because that produces HCl, right? So that's not a concern with other reactions, because with the anhydrides, right? So again, you're going to do a reaction. Here's your alcohol, ethanol, right? So again, the ethanol, the OR, right, is the nucleophile, is going to attack. Leaving group leaves, right? And the leaving group is an acid, but is acetic acid a strong enough acid to mess with my reaction? Not really, right? So you don't need to have the same concerns as you would with the acid chloride byproduct. Okay, does that make sense? So again, the alcohol is going to attack. Question?
Do we have that?
It's not on.
You have an extra.
Should I skip? Then, if I skip, it's because I've taken it out, so you can cross out if you have an extra one.
Okay.
Yeah. All right. And then, of course, you can consider, right, a cyclic, because we talked about these as well. So if we have those cyclic anhydrides, right, we can have a similar reaction. We have the alcohol, right? The OR is your nucleophile, so that's going to attack. Right now, the leaving group is attached, right? So you're going to break this bond, right? Or this bond, I guess that's the way they did it, but it's symmetrical. Either one is fine, right? And it's going to then leave you with an acid on one side, right, which would be your leaving group, okay? And then your new, right, the alcohol nucleophile over here in your ester. Yeah. No? Just, that makes sense? So if you have a cyclic anhydride, these reactions, they are going to give you that acid attached. But it's still, right, considered the leaving group. So this is the anhydride reaction. So what about alcohols and alcohols? Can we react, esters and alcohols, right? So we consider that the leaving group, right, or did I go too far? Oh, this is aspirin. So this we're going to do in lab, and I don't know, I know this week you'll finish the lab from last week, so this might be the next coming lab, and it's not from your lab book, so or Dr. Johnson will have a handout for you. But that reaction is with salicylic acid, right, and salicylic acid does have a carboxylic acid group, but that's not the part that's reacting in this situation. Here we're using the hydroxyl, right, the alcohol, to again, right, attack the acetic anhydride, right, the leaving group leaves, and then you have your product, which is acetylsalicylic acid, which we know as aspirin. Okay, and then of course you get some acetic acid as your, right, leaving group. So we're going to do this reaction in lab. And this is one of the acceptable routes. It is not the only way to make aspirin, and that's what the handout talks about, is that you have options and you'll get to choose if you want to try this reaction or if you want to try one of the other possible reactions to make aspirin. But what happens when you have an ester and then you have an alcohol? Okay, so that's the next group. So now you're going to have what we call a transesterification reaction, because would you agree you're starting with an ester, but you're making another one, a different ester, right? So this ester, what's the leaving group? Right, the OCH3, the methanol, right? So you're adding this new alcohol, right, to make a brand new ester. Does that make sense? So this is called a transesterification.
I was about to say, isn't that the Fischer?
It is not the Fischer, because the Fischer, you have to start with an acid first here. The Fischer, this would be an acid. This is an ester.
Oh, yeah.
So this is an ester reacting with another alcohol to make a different ester. So that's why it gets the name transesterification. You're basically transferring, right, your alcohols. So this is a possible, again, if you're thinking about making aspirin, this is a possible reaction if you wanted to try. So we'll get to, or not me, I keep thinking I'm going to teach the lab, but Dr. Johnson will talk to you about this. So this is one of the possibilities as well. Okay, and then notice that amides and nitriles, they do not react with alcohol. So we are not going to obviously discuss those reactions because they don't occur. Okay. So what about reaction with ammonia? So now what's the nucleophile of ammonia?
D, NH3.
Right, so that's ammonia. So what's going to be the nucleophile? Right, what's the trend? What am I removing to make a nucleophile? An H, right?
NH2.
So this is going to be NH2, again with a minus. Right, so does it make sense that that's what I'm adding, right? So again, I'm starting with my acid chloride, which is my most reactive because it has a wonderful leaving group, right? So the NH, right, the NH2 attacks, opens, closes, leaves, right? Same thing. So what you add is an NH2, the nucleophile, right? And then of course you have two ammonias, right? Because a second mole is going to be forming my salt, my ammonium chloride salt. So why 2 moles? Right? Because one is going to act as the nucleophile, the other is going to act as a way of forming the salt with your leaving group. Okay, this also works for acid anhydrides. So again, the nucleophile, right, ammonia attacks, opens, closes, and then, right, a leaving group. Okay, and again, it's going to couple with another ammonium molecule. So this is ammonium, right, acetate, the ion. So this can happen with ammonia, which is shown here, but also primary and secondary amines. Okay? So up at the top, we're showing you just ammonia here, but this could also be NHR, right, like a NH2R, So there could be a carbon chain associated there as well. Okay. So what about esters? Okay, so esters do react with amides, but again, they're less reactive, okay, than the acid halides and anhydrides. So again, you're going to need to heat it. It's not shown here, okay, but you do need usually heat in a higher concentration of ammonia. So excess of the ammonium is usually seen here. But again, same thing, right? The nucleophile attacks, open, closes, leaving group, right, which is the alcohol, ethanol in this case, leaves. Okay? And again, amides and nitriles do not react with ammonia or amines, so we don't see those reactions. So what other things can I do? Right? So what about acid chlorides reacting with anhydrides? Right? So how can I form anhydrides? Well, I can see the acid chloride, right, reacting with the salt, right? Where did I get this from? Salt of a carboxylic acid.
Oh, you have your carboxylic acid and
The base, right? So sodium hydroxide, right? Na from the sodium hydroxide here. So I would react my acid with a base, sodium or potassium hydroxide. I would get the salt, and now the salt again, right? That's going to be my nucleophile, right? Leaving group leaves, and you get an anhydride, right? And then of course the sodium associates with the leaving group, the chloride. So this reaction only occurs with the acid chloride. It does not work for anhydrides, esters, amides, or nitriles. So it only occurs with the acid chloride. Does that make sense? Again, right, look at for what the nucleophile is. And it's that acid, the ion of your acid. Okay, so that kind of leads us then to a summary slide, right? So if we really think about this, all we've been doing this whole time is interconversion. Would you agree? We are taking an acid chloride, adding water, we make the carboxylic acid, right? We take an ester and we add ammonia, we make an amide, right? So really all of these reactions are what we call interconversion reactions, and they can be summarized in this table right here. So you probably, again, noticed that the acid chloride with that great leaving group is the most reactive. So using acid chlorides, I can make all of the other groups, right? I can make the anhydride, we just saw it in the previous slide. I can make the esters, I can make the amides, I can even convert them back to the acid. Does that make sense? So the acid chloride can be interconverted into any of the other derivatives. Does that make sense? So what's the next most reactive? The anhydride, right? So the anhydride can be converted to an ester, to an amide, to an acid, but it cannot be made into the acid chloride because it's more reactive. Does that make sense? So the interconversion is always between, right, the most reactive and the nucleophile that's going to make one of the others, right? And then you can see ester is next, right? It only reacts to go this way, doesn't go back, right? Does that make sense how this table works? Right? And it's the note is on here at the bottom. The more reactive groups can be converted to less reactive groups, but it does not go the other way, the interconversion. Okay. And then, of course, most of these reactions, right, are going to give you the acid, right? And of course, if you get the ion, you can just add, right, a dilute acid or an H+, and you get it back. Yep, and you reset it to the acid.
or the
Okay? So the carboxylic acid. So that's really, I mean, you know, we've talked a lot about reactions here, but we've really just been converting one group into the other. So there's only a set of reactions, and there's a direction in which these reactions can happen. Does everybody see that? And it has to do with the reactivity. Okay? Now, what about some other things? So what other nucleophiles can I use, right? That's really what I'm trying to consider. So what else can I use to attack my carbonyl, right? use the leaving group to reform the carbonyl and get myself a new product? Well, one of those is the Grignard, right? So again, R, right, a carbon chain with the Mg, and it's usually bromine, right, or bromide, okay, but it can be chloride as well, so that's why it's MgX, right, X being a halogen there. And so I can use, right, 1 mole of my Grignard reacting with the carbonyl, right, let's say of an ester, okay, that's going to then give me, again, right, the R group is the nucleophile, right, of a magnesium. The magnesium bromide is going to be the salt that's formed there. Okay, so the R attacks, right, opens, right, forms the salt, but then remember the double bond forms again, right, so it closes as the leaving group leaves, right, and in this case the leaving group of an ester is going to give you the alcohol. So right now it's still the salt, but then I'm going to add H pluses and that's going to give me the alcohol. Okay, so I can actually add a carbon chain and get myself a ketone, right? So that's actually the product of a reaction between an ester and a Grignard is a ketone. Does that make sense? Again, got to figure out what's the nucleophile, right? Now, what if I had 2 moles of my Grignard? Would that make a different product? Sure would. Right? Because remember, the Grignards also react with aldehydes and ketones. We talked about this in chapter 16. It was a main reaction there. Okay, so if I had an additional mole, so once I made my first reaction, I could do a second reaction with my ketone product. So I wouldn't actually get a double bond, I would get an alcohol. Because would you agree the ketone that's formed does not have a leaving group, right? So I would not be able to reform my carbonyl. Does that make sense? So you do want to pay attention to how many moles you're given, okay? And then of course if you start with formic, just 1 carbon, then you'll get a potential of getting a aldehyde. So that's this one here with formic ester, you get an aldehyde, and then you get a secondary alcohol as the product. With any other ester, you get a tertiary alcohol because you form a ketone. So that's the difference between 47 and 48, right? This has a hydrogen here. I didn't make a note of that here, right? That H is going to give you an aldehyde as a product, and then the aldehyde, when it reacts again, forms a secondary alcohol. Right? Any other ester is not going to have a hydrogen here, right? It's going to have an R group. So it's going to give you a ketone, and then the ketone, when it reacts again with the Grignard, is going to give you a tertiary alcohol. We already went over this in chapter 16, so you can go back and take a look at that as well. Okay, so the second mole that's shown here, so once you formed your ketone, right, as that first mole reacted, the leaving group is gone. Okay, the second mole, again, the R is the nucleophile, right? It's going to attack open, right? Forms the salt, but then remember, this is going to close, right? Can't close back, excuse me, because, right, R's are not good leaving groups, so they have to stay, right, as alcohols. So we would not see it closing into the carbonyl. And of course, just to finish out the alcohol, you would have to add HCl in water. And then of course, you can do the same reaction with the lithium, right? Organolithium compound. What's the nucleophile of organolithium? RLI. It's R, right? Does that make sense? I mean, I don't know. I keep saying this and I see blanks.
Yeah, it's fine.
I know, for me too, but I hope you can make a note on the side of your notebook. Go back and think about this again when my brain is ready for learning. That the nucleophile, right? The key here is to look at these, right, available reagents and figure out what is the nucleophile, right? In both the Grignard and the organolithium, it's going to be your carbon chain, what we call the R, right? The R group. Okay, so again, the R is going to be the one attack, right, open, close, leave, right? But when you have 2 moles, it's going to attack again. Does that make sense? And that's why you see the product as an alcohol and not as a carbonyl. So you do want to make sure you use, right, 1 or 2 moles, right, appropriately, depending on how you want your product to look like. Okay, so please make a note. Think about this. What about Gilman's, right? So Gilman is another organometallic compound that we talked about as a possible reagent for the carbonyl attacks. And remember that the Gilman now, what's the R? It's really R2, right? But remember, it's only one of them, right? So the CH3, one of them attacks, open, close, leaves, right? So what you're adding new is just a CH3 group. Right? So the Gilman, if you recall, that's that copper lithium. And you end up with, right, again, the R, it's what's in the parentheses, which you have 2 of, but you only use 1 of them. Now notice the temperature, right, -78, which really means that with acid chlorides, this is really reactive. So we actually have to lower the temperature in order to control the reaction. So that's why you see that -78. So this has to be done in pretty cold conditions, very reactive. Yeah.
So if it wasn't -78, what would it do?
Then it would attack.
Oh, it would
Just keep going. And usually what happens is then the reaction, so in organic chemistry what we usually say is that it melts. So it, just everything comes apart. So we don't usually get our products. So there's just too many, it's going to happen so fast and too many options there. So
we need like dry ice or?
Yeah, so this would be a bath, like acetone dry ice bath, and then that lowers the temperature far enough. So not like an ice bath only goes to like 0, a little bit below 0, but if you use acetone in ice, dry ice, then you can lower it further. So that's Gilman reaction. So in Gilman, they only react with acid chlorides. So they don't react with anhydrides, they don't react with esters, they don't react with any of the other groups, amides and nitrile. So if you had a molecule with both the acid chloride and an ester, right, nothing is going to happen to the ester. It's just going to, right, stay the same because it's not, the Gilman only reacts with the acid chloride. So, and again, the Gilman, right, the CH3 in this case is the nucleophile. So what else can we do? Well, we can do reduction reaction. So remember, reduction is going to, right, take my double bond O, right, and it gives me either alcohols or it can give me the alkanes, right, single bond CH2, okay? And so we have a number of different reagents, and lithium aluminum tetrahydride is one of them, and this is the most commonly used. So as you see the example here, I'm starting out with an ester, and then if I add the reduction agent there, lithium aluminum tetrahydride, you get your alcohol. So what's the nucleophile in lithium aluminum tetrahydride? Hydrogen, right, which is actually in the form of a hydride, H-, right? So that's kind of uncommon, not all reagents, but lithium, this is a nice one to know as well, right? It's going to be the nucleophile, H-. And I have 4 of them, right? It's H4. So there's lots of hydrides available in this reagent. So you get, right, the alcohols there. Of course, the leaving group is the methanol, and then the, right, alcohol that came from your carbonyl, this one, right? This one leaves, right? The hydride attacks, open, close, leaves, you get the methanol, right? And then another hydride comes in, right? Open, but it can't close because there's no more leaving group, so I get my alcohol. So that's the reaction there. So it's showing you again here the steps. So you see the hydride, the H minus is going to be your nucleophile attacking the carbonyl, right? Then the leaving group leaves, okay, and you get that OR minus, and then of course that associates with the hydrogen to form your alcohol, the leaving group. And then in step 3, another attack, right? Opens, but there's no leaving group now, right? There's nothing to leave, so I can't reform the double bond, so I get an alcohol as the product of my reduction. So that's lithium aluminum tetrahydride. So what about sodium boron tetrahydride? Okay, this usually does not reduce esters. Okay, so again, you can use this one right on the carbonyls, like aldehydes and ketones, but it is not going to react with your ester. So that's, again, that term we've seen before, selective reduction, right, where I'm only going to reduce the carbonyl of the ketone. I'm not, right, reducing the ester. So you have to use lithium aluminum tetrahydride if you want it. Now, would the lithium aluminum tetrahydride affect the ketone? Get your reaction sheet. All right, so what about this one here? So an ester. Now, what if I want to get an aldehyde? Usually I get an alcohol, but what if I wanted to, right, get an aldehyde? So again, here's the ester. Okay, but I don't get an alcohol, I get an aldehyde, so I can use diisobutyl aluminum hydride, DIBALH, okay, for short there. Again, low temperatures, this is a very reactive, the two combining is very reactive, and so you have to lower that temperature, but then you can actually stop the collapse of your group, so it doesn't really go. That second attack doesn't happen. So you do have an option there of keeping your carbonyl. But if you use lithium aluminum tetrahydride, you will always get the alcohol. So if you don't want that, if you want the aldehyde, you have to use this different reduction agent. Okay, so what about amides? So amides do react lithium aluminum tetrahydride in the reduction, and now the reduction product, it basically, right, gets rid of the carbonyl portion of the amide, leaving you with an amide. So that's the product of the reduction of an amide is an amide. Again, right, the carbonyl part gets reduced, right, and then you get just the amine there, right, nitrogen with a carbon chain. Okay, and that's with lithium aluminum tetrahydride, and here's the mechanism. Again, the hydride is the nucleophile, so it attacks the carbonyl. Okay, but notice that then, right, so the first is here, but then something different happens. Okay, the O interacts with the aluminum. Okay, and so it forms that bond there, right, which we didn't see with the other groups. Okay, and then you have a redistribution because nitrogen can form that double bond, right, the shift base, the imine, right, and it forms that ion there. And when that happens, then you can have, right, another attack here. You get rid of the oxygen in this step, and then you can have another hydrogen come in, right, hydride, excuse me, and then it opens the double bond to give you the amines. So why doesn't this happen with an ester?
Because the nitrogen is what helps stabilize that.
Well, oxygen also has a lone pair, right? That could do the same. Why doesn't it? Because it's more electronegative, so it'd rather keep the electron pairs to itself. Nitrogen is less electronegative, so it's willing to do this, right? Oxygen would rather keep the lone pair to itself because it is more electronegative. So that's why we don't see the same pattern for esters that we see for the amides. Okay, and then nitriles can also be reduced. So the cyanyl group, the C triple bond N, again lithium aluminum tetrahydride, will give you the amine as well. So again, amides and nitriles tend to do similar reactions. You can see in their product. Okay, but again, this chapter is really about understanding these interconversions, and so this is the problem that I leave you with to try out at home, and I'll discuss the answers with you next time. But again, you're starting with an acid, and I want you to tell me what reagent would I need to use to get my acid chloride? What reagent would I have to use to get an ester like this, right? Methyl ester, right? What would I need to get the alcohol? And then, of course, these can be interconverted into other groups. Okay, so I'll leave you with this slide. Okay, and this basically summarizes most of the reactions that we did here. All right, so this is the last slide on chapter 18, and it's those interconversions. So I asked you to, take a look at this, and again, when you really look at all of these reactions that we went over in this chapter, they really, are just converting one group into the other. And so I just wanted to I thought this was a good summary slide to show you that. And so, the listed there, A, B, C, D, E, F, G, H, right, are the reagents that you would require for these interconversions. So I just wanted to go over that with you. So what do you think we would need to use in A? So we're starting from acetic acid. So so that's thionyl chloride, right? So that would be A.
And then would you just add ammonia for C? Ammonia.
Chloride, right? So that adds the Cl, right? So that's I've got a little dyslexia. SO2. Cl2.
Can we draw it? That's what CO2, because it explains why it does it.
Why it does what?
Why it adds the chlorine.
Yeah, there's two chlorines, so the chlorine, one of them is going to be able to be added to the acid. So that's A. And then what's happening with B? So we're taking now the acid chloride that we made in A, and now we want to make an ester. So what would we need? Right. So again, you've got to consider you want to add this as a nucleophile, right? Where's that going to come from? An alcohol. And what alcohol would that be? Right? Methanol, right? MEOH. Does that make sense? And of course, you would require a catalyst. And again, you can either use H plus or you can use a base, right? Does that make sense? So what about C? So in C, I think I heard it.
Ammonia.
It's ammonia, right? So now you want to add that NH2. So ammonia, right? And it's usually 2 moles of ammonia, right? Because remember, one of the moles is going to react, or it's going to get added as the nucleophile, and the other is going to neutralize or, add on to the Cl to make that salt, the ammonium chloride. So what about D? So D, we're going back to the acid to make an ester. So that's a special type. It's called the Fischer Esterification.
Yes.
It's an acid plus alcohol, right, in the presence of
H2SO4.
a sulfuric acid usually, right, as the catalyst.
So methanol
That's,
and H2SO4.
Yeah. Sorry. Does that make sense? All right, then E, so taking an ester, what would we have to add to make ammonia again, right? So it's really the same reagent. Is it 2 moles or 1 mole? 2 moles or 1 mole?
E? You need 2 moles?
1 mole, right? And you add water with it. Right? So that's how you're going to generate the alcohol again, right? With the H. All right, so we did E, now F. So we go back to the acid, and F is what kind of reaction? It's a reduction, right? So we're going to reduce, right, our carbonyl, and remember that there's a particular reagent we want you to think of. Which one is that? Lithium, right? So lithium, aluminum, right, tetrahydride. And really, that's the same as G, right? And that's the same as H, right? You would use the same reagent. These are all reductions, would you agree? Right? You're getting rid of the carbonyl, right, by adding, right, a reducing agent. So really, F, G, and H would all be the same. Does that make sense? So, you know, when it boils down to, and that's what I've been trying to do, is kind of summarize it for you and show you that, hey, I know we've talked about a lot of stuff. It's not trivial, but it's really, I mean, it can be easily summarized into one slide. Pretty much, you know, most of the reactions that we did in this chapter. And so, you know, if you really focus on finding that pattern that I've been trying to get you to identify, right, what are you adding, right, what's that nucleophile, right, what's getting put on, right, that you can then, you know, think about which reagent that would be required. And then, of course, for the reductions, it's mostly in this chapter, the useful one is the lithium aluminum tetrahydride. Okay, the others will reduce like the carbonyls of a ketone or an aldehyde. So, you know, you might want to go back to those other chapters if that's required. But really, if you think reduction in chapter 18, it's really lithium aluminum tetrahydride. Yeah.
For B and D, I get that you would need it. You need H2SO4 for the OH. Is it because chloride is more reactive that you would only need basic acid?
So chloride, I mean, and sometimes you don't even need any, you know, catalysts in there. But yeah, the chloride, the acid chloride is definitely, you know, most reactive out of all of the derivatives. So you don't usually, but for the D, that's, you know, a required. If you don't use the acid catalyst, that reaction doesn't work. And a base catalyst isn't useful also because it reacts with your carboxylic acid. So again, you would end up, you know, not getting a good yield from that reaction. So that is the specific, you know, reagent that gets used, or the catalyst that gets used as the reagent there. So.
And OH isn't as reactive. Yeah.
Yeah, and
OH isn't as reactive as chloride, so
yes,
you need a
the
stronger
OH
acid.
is not as reactive, exactly. So again, you know, just wanting to find ways of sort of taking this information and not, you know, being overwhelmed by it, but finding a way to, you know, study this in a reasonable way. And I think that this is a good slide there. So that's all that I was really going to do on the computer side. I didn't even think I needed my computer today because we're just going to review then.